Hi everyone, my name is Blaze and I will be taking you through how to estimate pi using random numbers in Python. If you've never seen or heard of Python before, it's just a computer language that's really commonly used. It's not that complicated, and in this tutorial I will not really be going into it very much in depth, and I will explain. It'll be a pretty simple use of the language. Anyway, these are just some of the libraries that we will use in Python or that we draw from in Python. They provide various methodologies that we can use, and it makes everything easy. Anyway, so our objective, whenever doing a math or a computer science problem, it's always important to define your objective so you can understand what the direction you need to go in order to accomplish this objective. And so for this, our objective is estimating pi using random number generation on a two-dimensional graph. And we'll do this by plotting a circle centered at 0.5, 0.5 with a radius of 0.5. We'll create a set of random points for x and y between 0 and 1. And so all of our points that we will generate will fall within the square of the unit square, I guess that you can call it. The number type for these kind of point generations in the computer science world is called a float. That's just the type of number we will be generating. These are just, these are just rational numbers essentially with limited decimal places, but we'll do this all randomly. Then we will find if the random point that we created fell within the circle or not. We can just do this by using the distance function. Since we know the center of the circle, 0.5, 0, and 0.5, if the point falls outside of the distance, or if it's greater than or equal to 0.5, which is the radius, it will not be in the circle. And so we can easily find this out. Then we will generate an approximation for pi using the differing numbers of samples. What this means essentially is like the number of times that the point falls within the circle. We will count that up and then compare that to the total. And so we'll get some percentage that fall within the circle, and we'll get some percentage that don't. If we can multiply that value in a way that I'll explain later to give us a pretty accurate estimation of pi. And then we'll graph it, so I'll give you some visual and stuff. Okay, so let's move on to plotting the circle. So our first part. So we know the circumference length, or the equation for circumference of a circle, and we also know the equation that relates x and y values to the radius of the circle. But this equation of the circle is not a function. So see if you can think how we might get the circumference by combining two functions together by using our knowledge of sine and cosine. But a good thing, that's for the mathematical world. A good thing, this is a computer science world, and so we can basically graph whatever we want. We can graph non-functions. But as an exercise, think of a way where you might be able to graph a circle using sine and cosine, and having those be in two different functions essentially, and then combining those functions together. So we'll do this. It's pretty straightforward in Python. We have this PLT function which draws some method, and this method will give us the fig size. And then we have theta. I define theta. We use theta in trigonometry as like the degree or the angle of which we want to measure some trigonomic function by. And so I define that. Don't really worry about this stuff. I just basically make theta be a number of different points or degrees around the circle. So if you look at this, I'm basically ranging theta between 0 and 2 pi, and p.pi is pi. We'll just think about that as pi. And I do it 100 times, so that's going to come up to a pretty even circle. That's the point of that. And so this basically gives us a whole range of thetas to draw from, and then we connect the dots of those various ranges of theta in our graph. So then we have x and we have y. This is just going to go along with how we define x and y to be on our graph. And so we have a y-intercept of both of these. We have an amplitude of this cosine and sine function. And when we draw this, it actually comes out to be a good circle. This is just logistical stuff and communicating with the program of what color to draw the graph and what our x and y coordinates are. But we just find that there. And so we see it like this. And if you notice, what I mean by we're drawing from various different types of theta, or various thetas along the circumference of the circle, you notice 1 pi is right halfway around the circle in the sine and the cosine world. Right? If we plug that into cosine or sine, we're only going to get halfway around the circle, the unit circle. Now, the value of sine and cosine will be different, but that's beyond the point. And so if I gradually increase this, we'll gradually draw a bigger and bigger circle until I punch in the full circumference of the circle. And that way we have points that go all the way around the circle. That's the idea there. And so now we have our circle. We accomplished our first objective, or first thing we wanted to accomplish. We wanted to plot a circle, which we did. Second thing we want to do is we want to create a series of random points between 0 and 1 in this case, or in the 0, 1 unit square. So what I mean by unit square is this square right here. We're going to create a bunch of random points, and we're going to judge if they fall within the circle or fall outside of the circle. And that'll give us a ratio that will help us determine or estimate pi. Luckily, in the computer science world, I can write a function where I can get the computer to do this for me. Note that these numbers aren't truly random. Don't know what happened there. As the computer draws its numbers from a stored database, but this will work in this case. So in order to get our pairs, we basically just tell the computer to make a list of x values, random x values. We tell the computer to create a list of random y values between 0 and 1. And we loop this a number of times, n times. So however many pairs we want to create, we just tell the computer to create this many random pairs between 0 and 1, and it'll spit it out for us. So it'll put x and y together to make a point, or a set of points. All right, well, now I should prove it to you that this function actually works. And so let's say I want one random pair. That'll give me this random pair of x value here, y value here. There's 1 point in this list, so there's n number of points. If I put 50, there should be 50 points in this list. And when I scroll all the way over, you can probably believe that is greater than the one pair that I create here. Anyway, I'm going to keep it as 1 for now because I want to show you all something. But I'll go ahead and store I'm going to store this as z. And so I will then store z as I will store the x values of z, and then I will store the y values of z. This is just how you do this in Python. It's basically taking advantage of the indexing that you can use within lists and lists of tuples, essentially. But that goes beyond the scope of what I want to talk about. And so just to show you what I did is I grabbed this x value corresponding here, and I grabbed this y value from there. So the next thing, so we created our random points, or we can create random points, however many points we want. So we accomplished our B. Now we'll move on to C. We want to test if the random point is in the circle or not. And one cool thing about the computer science world is if you run a function, and if the function is true, it'll return true. And if you run a function and it's false, it'll return false. And true is the equivalent of 1, the integer 1, and false is the equivalent of 0. And so we'll take advantage of that here. So we want to test if the random point is in the circle or not. We're going to use this point z. But we know, so we know the distance between the 2 points, x1, y1, and x2, y2, and its two-dimensional space is given by this function right here, the distance function. This should look familiar. And so essentially, if the distance of some random point is greater than 0.5, and the center of our circle is 0.5, based on how we defined our circles to be, it's clearly not going to be in the circle, and I'll visualize that below. But that's the idea. And so we define our circle here. We use the equation for the circle. So this is the radius, this is the x shift, the y shift. And I just drew up a quick in-circle function. And so here should look really familiar to this equation right here. I just added an inequality here. And in Python, this is equivalent to the exponential command. So that's just what that means. But basically, if some points of numbers that I plug in here, or values for x and values of y that I plug in here, if this returns true, or if this is true, it'll return true. If it's false, it'll return false. That is, if this is actually greater than r squared, it'll be false. But if it's less than or greater than equal to, note that like we're going to define that the circumference of the circle is not actually in the circle. So if you get a random point that falls right on the circumference of the circle, we're going to say that's not in the circle. So we're just going to define this as everything less than or equal to r squared. If this value holds true, the value will be in the circle. That's the idea. And so that'll return true. We'll run this to make sure I didn't mess up anything there. It looks like it ran okay. And so let's test it out. So we know our center of the circle point. We know that this is in fact in the circle. And so let's go ahead and test and see if our function works. Okay, it thinks it is in the circle. Awesome. Now let's test and see if our 1, 1 is in the circle. Well, that's false. Well, okay, let's conceptualize that real quick. The point 1, 1 is right here. That's clearly not in our circle. So it looks like our function is doing pretty well here. Now we're going to test this on our random point that we generated a second ago. So zx, zy, I saved those values as. So we'll test if this point is in the circle or not. Okay, so it looks like it is. So 0.15, 0.46, so 0.15 and 0.46, that would be around here. So that looks like it's true to me. So I think we can trust our in-circle function. Where am I? Cool. Now that we know how to test whether a point is in the circle or not, we can actually have it all to come together and approximate pi. So I think this is actually part D. So we'll label this appropriately. So we can approximate pi by putting essentially everything that we've done up to this point together. And I'll show you how. So observe that the areas of the circle and the square and the randomly generated pairs are related by this. So area of the circle over the area of the square. Well, we know the area of the circle is pi r squared. We know the area of the square is 1. So that's, if we move this 0.5, this is really just 1/4. If we move that 4 to the denominator, we're going to get pi over 4, which is going to approximately equal the number of points that we randomly generate to be in the circle versus the number of points that we create in general. So just the total number of points we create. And so this will be the same thing. This ratio should be about the same as our pi over 4. And so hence, pi is going to approximately equal, based on our luck essentially with random number generation, 4 times the number of pairs in the circle over the number of pairs generated. So using this equation in conjunction with your functions from part A and part B above, we can generate and more parts. I should just delete this, parts above. We can generate multiple different approximations for pi using, say, 500, 550, 500, 1000, and 500 samples by just saving the number of times that a random point turned true out of the total number of points generated and multiplying that decimal by 4. I'll show you what I mean here. So let's go ahead and count the number of random points we create, how many of them fall within the circle or not. So I created this function called counting. The purpose of counting is just to count whether the random points or point within a list of points fell within the circle or not. So I go ahead, run this pairs. I create a bunch of random pairs or n number of random pairs, and I create this counter. And this counter is going to count how many are in the circle. And so basically what this is all going to do is generate or index a bunch of y and x points that we created from our function that we created above and see if they fall within the circle or not. And if they do, it'll be plus true or plus 1. It'll return plus 1 or it'll return plus 0. When I say return, I mean this function will return. And so our count will go up or it'll stay the same. If it's false, it'll go up. If it's true, by 1. And so we are essentially just counting the number of trues we get for each random point we generate. And so if I go ahead and run this, you'll see that it runs correctly. So if I say, okay, I want to create 50 random points and I want to know how many of these points fall within the circle, I can just plug that n equals 50 to right here. I'm going to save it. This is just how you save stuff in the computer science world. And we'll go ahead and print it. Print just shows you what it is. So we created 50. We want to count how many of those 50 random points fell within the circle. And so we found 40 number of points out of 50 random tries for 80% accuracy. I should get rid of that. Let's see, where am I? 0.84 accuracy. So if I wanted to convert this to percentage, I would have to multiply it by 100%, resulting in a pi approximation of 3.36. And so this 3.36 we got from multiplying 4 times this percentage right here, or this decimal. So we got 3.36, so right, pi is about 3.14, so 50 wasn't that accurate, or we'll compare it to n equals 500. So we'll do the same thing here. See, we still weren't that close, 3.008, but I think this seems a little closer than 3.36. Let's try it for 1,000. 3.108, so that's pretty accurate, and you can see how that is more accurate than these previous two. So we have this thought that maybe with increasing random number generations or increasing samples that we use, the more accurate our prediction is going to be, and that makes sense, right? So now we can all grab this visually. This is just going to be a lot of Python code. This is just how you plot stuff, these commands. These are going to be our x values and our y values. Oh, this should look familiar. This is just the circle we plotted in part A. This is our list, and so a list of different counts of random numbers we want to generate. So basically for one round, we'll create 50 random numbers, 500, 1,000, 5,000, and we will graph those all respectively. So that's the idea. And look at that. So this is our 50. So we can see 50 random points. We go up to, what did we have? 500. These are 500 random points. 1,000 random points, 5,000 random points, and our unit square, I guess, is getting pretty filled in. But you can see that it would make sense that with more random points generated, and if they fall in the circle or not, you're going to get a closer value of pi estimation. Anyway, that's it. I hope this was a cool little exercise. I'll go ahead and link this Google Collaboratory link in the description so that you can have access to it if you'd like. Google Collaboratory is just this Google-based platform that you can use essentially for Python writing and things like that. Anyway, thanks. Hope you enjoyed, and tune in next time, I guess.